Alright, so this is our final chapter in dynamics. And we will go into, of course, after studying particles, impulse and momentum, we will go into rigid body, impulse and momentum. We'll start with the linear impulse and momentum for the systems of particles. So when we think about the total momentum, it's just every time we think about total, we're just summing them up. So what are we summing? We're summing the linear momenta of the individual particles, okay, making that system. Again, this is a very incredibly powerful phrase. And when we say system, even though for mechanical, of course, the rigid systems, you also have to understand that there are non-rigid systems, which kind of behave pretty much like the rigid system, by the way. It's just the factors are a little bit different. That's about it. So you may also use the total mass and the velocity of the system's center of mass. Why do I have to tell you mechanical also going into the chemical stuff? Is because now in our field we're getting into the soft robotics and soft systems, which we try to put the mechanical system into the living things. So anyway, so you may also use the total mass and also the velocity of the system's center of mass. Okay, so how do we do that? We're going to use, of course, the momentum total. So therefore, you are going to add all of the system momentum of each particle. Add them up and you will get that. And we can write that down into a very simple way, your mass and then your velocity of that total momentum, okay? This means like we're totaling up. The total impulse, the same thing. We're going to take the total, so the impulse applied by an equivalent resultant total force, okay, applied to the system. So here this thing is not for just one particle or rigid body. Is made of many particles in that rigid body. Okay, so total impulse, we're looking at the change in linear momentum of that system. So we do the same thing. Our interval, our sum force is equal to the change in momentum, okay? And we're gonna write it in an extended way by showing the long form of this, okay? So that's your sum of the momentum for each particle in that system. The same thing. That's your final, and this is your initial. It's the same thing, we're just adding sum into it. And then of course we can write the total velocity and the initial and the final condition. Okay. So after studying the particle impulse and momentum, it's pretty easy to add the systems of particles into it, and you will get the rigid body impulse and momentum. So total angular momentum, we do the rotation. We are going to treat the same way, sum of the angular momenta of the individual particles. So here is your momentum, angular momentum, okay, your R, and then your linear momentum. We're going to write it in an expanded way, but everything is the same. We're only adding this systems of particles. You can also use the position, velocity, and mass moment of inertia of the system's mass center. So if you have a system, of course, we do have the mass center. So we will definitely take a look at the inertia of that system mass, right? Moment inertia of the system mass center in this way. So you have your momentum, angular momentum. We're going to write it in an expanded way, your R, then times. This is for all the particles, okay? We're just writing it that way. And then of course mass times your total velocity plus your you're gonna see this angular momentum is connected to this angular velocity, and then of course your impulse moment of inertia is going to be right here. So this is the only extra part that is added to the angular momentum calculation. Total angular impulse is nothing but the sum of the individual force impulses. And we can write the equation to represent that definition in this way. So forces, they're going to act at different location. Yeah, here these are different forces and a different location represented by I for the particles, okay, in that rigid system. And here is, of course, your impulse, angular impulse. We can also write it with a moment in this way, your time interval, and then the sum of your moments equivalent to this, okay. Angular impulse momentum principle applied to the system again is equal to the change in angular momentum. So here is a change and it's going to give you your impulse. So that relationship is called angular impulse momentum principle. And we're going to write the impulse in a moment and we're going to write the change in momentum in a momentum way. Yeah? Initial and then your final condition. Expanded, since they are sum, we're going to represent with the I particles, yeah, and calculate each one of them, and then of course put it into this equation will give you this change in momentum, which can be equivalent to this angular impulse, yeah. So we can be able to calculate anything we want out of these factors, okay. Then the very first example of chapter 10, so your horizontal force, this guy is applied over a small interval of time, meaning this little interval of time. And you have a system of particles in the situation shown below. You have only two particles right here, A, B, C, and D. And we have to rank it. And we're going to rank the magnitude, and we're going to rank the change in linear velocity of each body's mass center from before the application of the impulse to after the removal of the impulse. Yeah? So let's take a look at, so this thing is going to hit here, that thing is going to hit there, and this external force is going to hit here, and this external force is going to hit here at that interval. Yeah? So let's see how we rank it. So we will definitely use this equation to be able to calculate, since we have a system of particles containing two particles. To simplify the system, we're going to have a sum of the force, okay? And of course it's going to equal to your mass times velocity, yes, and then you're going to minus the mass times velocity of the final and the initial position. Okay, so how do we do that? So let's take a look at it. This is hitting right here. So since we are concentrating on the change in linear velocity, I have a paper cut on my finger. It's pretty difficult for me to draw a line here. So anyway, so we're looking at the change in linear velocity. In order for us to be able to calculate that, you have to come up with the impulse, momentum principle, which we have just all learned. And you can be able to use this equation, of course. So when you look at this first, right, case A, you're going to see mass is m, your impulse is f delta t, yeah, and so you can be able to calculate the change in velocity, by using that equation. I can write that back down for you. It's gonna look like this. If you write that down in a simple way, f and then delta t divided by m. Okay. All right. Then of course we're gonna write the same thing here. Your mass is m, and then your impulse is this guy, which is force time delta t. So you will be getting the same as this, which is your change in velocity, linear velocity is your f delta t divided by m. Regardless of where you apply the force, is here or here, okay? Because your velocity just depends on this amount in the mass, doesn't depend on where you apply it. All right, C, we're gonna write the same thing. Your mass is m, impulse is this time half. So we're going to get something like this, okay? we will get half of that, A and B. So I'm just going to write it very quickly. All right. Then D, we'll do the same thing, and this time you have your masses 2 times. Yeah, so therefore we're going to give it just like that. So you're going to have F delta T. Your mass is 2 times, so you still have half here. Yeah, you can take this out, which is exactly the same as that. So this one, yeah, so I get it like AB, and then CD is gonna be the same. So I don't know why the textbook is giving you the wrong thing. That's what I got, yeah? All right. Then we'll go into rank the magnitude of the change in angular velocity. And we want to rank change in angular this time, yeah? Of each body before the application of the impulse to after the removal of that impulse. So let's take a look at it. And this time we're going to use this equation, yes? And of course, you are now concentrating in angular velocity, therefore, yeah, we will change the equation from the linear into angular. So we're going to do the same thing. This time your velocity is delta, omega, okay? W, so we will do the same thing. You have your F delta T, and then divided by M, and this time you're going to have a little r, yeah, instead of just a regular M, because for rotation you have a hand r, yeah, the distance between the point O and then to the linear velocity. So we're going to do the same thing for B. Okay. Before I go into B, I want you to get this, okay? I'm too fast in writing like that. You would initiate this way, okay? Don't get stuck like I do, because I can see it I can see it faster than you do. So do this way, okay? FR, because your force, yeah, is not now angular, so therefore you still need to put this little thing, and then your IG, of course, which is this guy, yeah, is your MR squared. MR squared is your IG. I use that way instead of just go straight to IG. So if you do like that, you can cancel this and we get that, okay? I'm just trying to show you how we calculate it. Your impulse again is at a distant r this time, but now you change, okay, the force where you apply. And unlike your linear, yeah, when you change the application or where you apply, they change, okay, the angular velocity, it changes according to where you apply. So now you have a 2 masses, and you have a I, okay, your mass inertia is higher because you have 2 masses, and it is applied at that center right here. So it's larger than A, but so delta, okay, this guy is gonna be smaller than the first condition, okay? I would say angular velocity of B is where's my eraser, compared to that, because we're ranking here anyway, is less than, okay, angular velocity of A. All right, then we will get into this guy is half, yeah, ft, and we do the same thing as in here. So you go like f, and then that is 0.5 f, and then you put r into it, and when you calculate that, you're gonna get something like this. Okay, that's 1/2, and then f because it's rotation, and then delta t, and then divided by your mr squared and you have another 2 here, yeah, because you have 2 masses here. Of course, we put a 2 here is when you study, yeah, the mass inertia, because it has a resistance to the motion, we can be able to put that in and calculate it. So 1/4 is going to give you like that, yeah, 1/4, and then you cancel r, so you're going to get like this, but 1/4 of it, which is smaller than a, okay, delta t, and then m, and then r. Then we have d. D is a little bit different from your c. It's because right now the mass, okay, inertia is mass movement of inertia is a 3mr squared. It's given there for you. So we do the same thing. So we calculate delta w, and of course this time you have fr and then delta t. I'm just writing this, but I put the r because it's rotational, and we're given the mass moment is 3 times of mr squared, and I put that in. Cancel the r, yeah, so you will get 1/3 of a. I would just say 1/3 of a, okay. So this is the highest, followed by 1/3 d, followed by 1/4 c, and then the last one is this guy, because it doesn't really identify what G is, IG is here, yeah. So therefore we take it could be the smallest. All right, the next one is a large force in x direction. This guy is applied to the system of particles shown over a small interval of time, this time. So follow the removal of the force. We remove the force. How do you expect the system to move? So this is your system. Where is it going to move? You apply the force right here. And you're given coordinates of x and then y. Let's see. And of course we have a statement here. So we will go into each statement here regarding, of course, the previously shown on problem in the slide. So first thing is you're gonna translate up, which is this guy, yeah, your position y, and then to the right, position x. So first you're gonna translate up and then to the right. So go down and then that way. So it means I go this way and then that, yeah. No rotation. I mean this system right here, because of that force applied that amount of time. That's not true, because you have something like this. If you apply the force at the end, it would definitely rotate. Okay, so therefore this is incorrect instantly. Translate to the right. So this guy gonna translate to the right, and it's not going to rotate. This is also wrong because of this without rotation. Yeah, so this and be immediately come off. So translate up, it's going to go up and then to the right, and then translate to the right, and then it's going to rotate counterclockwise. Yeah, there's a rotation, but then translate up and then go to the right is, it can't happen, you know, because it's just against the rule, because you're hitting at the end like this. How can something that's been hit at the bottom will go climb up? Yeah, so therefore this is wrong. So the last answer is to translate to the right, you're going to translate that way. At the same time, rotate. Yeah. You're going to go counterclockwise, actually. Go this way. Okay, translate and then go that way. I draw it a wrong way. I can draw this again. Yes. You're going to translate to the right. At the same time, you're going to rotate counterclockwise. And that's a better one. Yeah. Okay. Then we will come into rigid body impulse and get into linear momentum and impulse. So let's see another question. So we have to write down the equation for the linear momentum of a part. That's kind of like a review. So you go, momentum is mv, and then if a rigid body is rotating, yeah, as well as translating, you're rotating, and then at the same time you're translating. We usually do like this, either go clock or anti-clockwise and translate. So do all the points on the rigid body have the same velocity? So since you're not dealing with just a single particle, but you're dealing with system of particle. So the answer is no. Not all the points on the rigid body have the same velocity. They will have different velocity. That's very common sense. How can the particle on this side will have the same velocity as there? Impossible. The system velocity is not the individual velocity in that rigid body. So if we apply the particle near momentum equation to a rigid body, so we apply the particle linear momentum equation to the rigid body. So the question asks you, what point do you think we should use for the velocity? The answer is center of mass. So basically it's just telling you that when you apply the particle linear momentum equation to the rigid body, you have to concentrate the center of mass, the point where your center of mass is, if you want to use for the velocity. So that's a typical thing that we do. Always pick the center of mass to handle the particle linear momentum equation in that rigid body. Then based on your answers to the previous question, which is center of mass, you're going to write down what you think is the equation. So I'm just going to you're going to very sensitive this slide is. So we're going to write down this equation. Of course, your velocity is at the center of mass, and we give it a g. Here, and that g is right here on this rigid body. And when you write it in a momentum way, we can be able to write mass m, going with the velocity, and we want that velocity reference to the g point. Central mass, rigid body linear momentum. So when you go here, your linear momentum of a rigid body, okay, you can express in terms of the body's overall mass and the velocity of that mass center, okay, which is simply written with that little equation. So now we will get into a problem. So you have a sphere moves down a smooth frictionless incline here, and we have to choose one of them, which quantity is going to increase. So you have angular velocity, you have total energy, and then you have potential energy at a height, and then you have your linear momentum, which is your m is your mass, so linear momentum is your mv. Okay, so here you have to review your something that you have to understand is your incline is mentioned frictionless. There's no friction that we have to worry about in this example. So this sphere cannot roll down, it's going to slide down. How weird that is. So your angular velocity, your sphere needs the friction to rotate. Without the friction, it will just translate. So therefore this will not increase, because this is going to stay zero for this example because of the frictionless nature of it. Now the total energy of the system, when you think about it, we're thinking about the kinetic energy and your KE, and then your potential energy, So your sphere is going down, and from a position, so there is a change in potential energy into kinetic energy. Since we're dealing with a frictionless, again, inclined, your energy is conserved, meaning like the potential energy when it was started is going to go into motion, which is kinetic energy. So that's also wrong. And your potential energy will not increase because it will be transferred into kinetic energy. Yeah. So therefore, your potential energy will decrease, not increase. This one will go down. Linear momentum, you have mv, and it is going with the velocity, so that will definitely increase because you're gaining velocity as you slide down. Okay, mass is a constant, so since the velocity increase, your momentum will definitely increase. Yeah, it's just you're looking at the mass is constant and velocity increases as the sphere slides down that incline, so therefore your momentum increases. Alright, that's a pretty easy. Yeah? So now your sphere is going to move down, but this time you got friction, yes, a rough incline. So which of the following quantities is going to increase? So we definitely know it's translating, so linear momentum. Now this time, because of this word, we're dealing with friction, so it will definitely rotate. So you do have the angular velocity as well. So they will increase. The rest of them stay the same. Energy is conserved. Potential energy decreases. Linear impulse, we go in to here, and we have linear impulse is nothing but your accumulated effect of forces. Every time we think about impulse, we think about the effect of the force, acting over the time. So here is your interval, your force acting over time is going to be your impulse, effects of force. Then we will get into rigid bodies. So you have a pencil, and that pencil is on a desk, and you're going to apply a force that will make the pencil roll straight. Okay, you're going to apply a force that will make the pencil roll and then rotate. Roll straight means just go like that, just roll. And roll and rotate is you roll and then you also rotate. So we have two different situations that can happen because of the effect of these forces. So here we will picture that. So principle of linear impulse and momentum is what we're going to use in this case. So the impulse of the resultant force acting on a rigid body is equal to the change in the body's linear momentum. Yeah. So this is just rolling pencil, and that's a rolling and rotating pencil because of the different effect of force. Okay. So of course we'll get into our equation, same equation, showing your force time interval expanded by using final momentum and your initial momentum. Okay, so here the point is that we are dealing with the principle linear impulse and momentum. Impulse, studying the effects of the force and how it is affecting the pencil in two different ways, and then what happened to the momentum, as the pencil moves with linear mv, and then linear with rotation is going to be mv and m m omega the whole, and which is this guy. What I'm saying is mv is for linear, and omega is going to be your rotational momentum. So then we will get into another system of rigid bodies, and we will see the total linear momentum. Every time we total it, we're talking about the sum, and we are dealing with a system of rigid bodies, so therefore we will use I to count, how many particles or rigid bodies are in there. Then your linear impulse, and we are dealing with the sum of their force in the interval. Okay, and we're talking about the sum of momenta, which is this guy, of the individual bodies. We deal with the particle, but for rigid bodies, we deal with different rigid bodies in that system. Principle of linear impulse and momentum. So here is your impulse. It's a change in moment. Your impulse is a change in momentum. And we can also write it in this way, the same equation that we've been using, time interval. And then sum of the force is equal to expanded version of it is the sum of the momentar, which is a final, and this one is initial. Yeah. And of course, you have many different rigid bodies here, denoted by the number of rigid bodies is I. So thus you're seeing the principle of linear impulse and momentum. Now let's take a look at the conservation of your linear momentum. So if we want to conserve, we gotta understand that if the external forces acting on that rigid body is zero, yeah, and over a time period, of course, your linear momentum is completely conserved, meaning constant. So here we can be able to equate, yeah, initial and the final situation in this way. Of course, we're dealing with the system, yeah, so therefore you still have your I to indicate how many masses you're dealing with in that system, and each one of them has its own velocity, and you are summing them up, and the momentum, yeah, in initial state is equal to the sum of the momentum in the final state. And that's all it's saying right here for the conservation of linear momentum. And the most important point is your external forces is zero. And now we'll get into a problem here. And here we're dealing with a particle, and that particle is traveling horizontally, and it's going to strike a rigid body, strikes a rigid body. So that rigid body is initially at rest, and of course it also sticks to the body such that that particle and body is going to move together after the collision or impact. Yeah. So here is your mass of your first body, and then it's going to hit with the next body, which is completely tandem, attached to each other, mass 1 and mass 2 with this. So that's your situation A, and of course hitting with that velocity. So you do have a momentum. So second is hitting right here at this location, and the third one is hitting half of your velocity, and the fourth one is hitting with double the amount of velocity. So let's take a look at it, and we have to rank it, and you want to rank it, rank the velocity of the center of mass of each system. So we gotta deal with the velocity, but that velocity is not like whatever particle. It is a particle or the location. We take it the center of mass location. As you know, in the rigid body, you have many different particles, and they have their own velocity. Now we want to deal with the center of mass, okay, location, and we will concentrate the velocity at that point. Following the collision from the greatest, and we're going to list it to the least. Okay, so first, of course, we will calculate. So the very first one, you have conservation of momentum. So you have, before you start with mv, after that you're going to get 3 of your masses going with a final velocity, and the velocity is at a mass g. Second one, we're going to write it the same thing. Started out with mv, ended up with 3m, and the velocity is g, okay? And then the third one, you start out with half velocity, ended up with 3m, okay, vg. And the last one, you're going to start out with double the velocity, and ended up with 1, 2, 3, 4 times of your mass, because this guy is 2 now, and then the final velocity. Yes. So when we look at it, this two equal, and let's see, your 1 by 2 is going to go to that side, so you're going to get 6, okay, 6 mv g2, and then here you're going to get mv is equal to 4 divided by 2, you're going to get 2 mvg. So that's what we're going to get. Of course, your question is asking for only velocity, yes, and your velocity is following the collision, okay, following the collision and not before. So therefore, you're gonna have to calculate this. Yeah. So if you look at it from the MV point towards VG, it will be looking the opposite of that. Yeah. So meaning like that, this is the greatest, and then followed by that, because that's 6 and that's 2, and then the rest. Since you're dealing with this side of the equation, it will be the completely reverse, and you don't even have to calculate it, just reverse it. So therefore, that will be the greatest, followed by D, and then C. Okay, so that's how we calculate. I know that some of the students will actually spend a lot of time by moving, this to the side and calculate, of course. So you would actually do this, if you don't flip it. So anyway, in science, we gotta do a lot of change in direction. And if your brain can be able to do that flipped very easily, you will save a lot of time. Okay, so you will be actually calculating BG like that. Yeah, so that's a long way. So you can just calculate like this. And since going for this direction, you're going, like least and then highest and then median. Here, then you can flip the whole thing because you're calculating something on the other side. All right. And there's nothing, it's just really straightforward, meaning like they both are multiplication on each side of the equation, so therefore you can be able to flip it. Yes. Then we will get into the angular momentum. So any rotating body has angular momentum, and of course we're dealing with the center, our reference point again, the center of the mass G. So rotating body, they always have an angular momentum here, and your angular momentum depends on these things. Yeah. Of course, your reference point, your datum reference point is very important. So it depends on pure translation, pure rotation, and both translation and rotation, we call it GPM, which is general planar motion. So pure translation, we use this equation. You have already studied that. The only thing that we change is this guy with respect to the point O, and you're dealing with the mass center, so we also have G. So we put that at the same time here. So your angular momentum is equal to RGO times mv. Pure rotation is just rotation, so therefore we can do the rotation. Angular momentum is your mass inertia with the angular velocity. GPM for both translation and rotation, of course, we still use the mass inertia, but we change the reference point to G, mass center, instead of just the point O in the system. Okay, that's a little bit different. And a lot of the students will have a confusion between the 2 points, but that's movable, many different points. This is just single point at the center. And then, of course, at times your angular velocity. Your general planar motion, now we're going to switch, any point in the system, from the only the point at the center, G. So now at point O, we will do the same thing as we did here. So your angular momentum is equal to R, and you have point at G and O, reference point GO times mvg at the, this is the velocity at mass center plus your mass inertia at center G times angular velocity. Okay, so since I'm not asking too much about it, the only thing you will have to understand is how we deal with the 2 reference point, and you're going to have to recognize the equation. Okay, so make sure that you might need to memorize this, if you cannot be able to make sense out of the 2 systems. It's just very simple. It's just where your reference point is. This is at the mass center, and this point O can be anywhere. General planar motion, again, are GO times mvg, okay? This is velocity at g. This is r that can come from g and o, and then of course time, your mass, will give you the translation motion, and that is a translation part of this GPM. Your rotation, you're going to get it from the mass inertia times, but of course that mass inertia is, we are dealing with the reference G, mass center, and then times the angular velocity. And of course we're going to put them together and you're going to get the previously shown equation, yes, this guy. So now we will go into, you're riding a teacup, right, in amusement park. So here is a teacup and it's not spinning about its center. But the base here, that base is holding all the teacups and that is still moving. So does it still have angular momentum? So you have to think about whether these teacups have the angular momentum of its own when your base is attached to the teacups. So it does have the angular momentum. That's because you're seeing like teacups are like the point in the rigid body system. The whole thing is your rigid body system. So each one of them is a single point. I would just draw it here with this a big giant teapot and surrounded by little teacup here, 1, 2, 3, 4. Yeah, so 1, 2, 3, 4, and then of course 5 on the other side. So each one of them is moving, with this whole system. So therefore you do have the separate angular momentum for each teacup. And the whole system also have its own momentum because they're stuck together and moving like that. So you can take this system based with your all teacups one angular momentum, and then you have each items on that base is your teapot and each of the 5 teacups, okay? And they're all moving with their own angular momentum. So make sure that you can be able to understand that as well. Then we will come down to write down the angular momentum equation of the teacup for this case. So we have to write that down. So we do the same thing. We're going to use our regular angular momentum equation at any point is equal to your distance from the center as well as from that point times mv. So if the platform stops rotating, but the teacups is still spinning, so does it have angular momentum? So what's going on here, the motion is this guy is rotating and that guy is spinning, like your solar system. So we're all orbiting around the sun at the same time. For Earth, we're spinning on its own as well, like that. Okay, so if the platform stops rotating but your teacup still spinning, we're going to understand if that, okay, does it still have angular momentum? Of course you do, because of the isolated system. Even though they're attached, you can still see this is moving with its own motion, so therefore you can be able to get its own angular momentum for each teacup because of this spinning motion. Now you're going to write down the angular momentum equation. For that case, is going to be just that, because we're not considering the base anymore. We're just considering the spinning teacup is going to be the mass inertia times the angular velocity. Then we will get into the next example, and you have a bar of mass m and length of L going to move differently in each of the situation A, B, C, and D. And we're going to rank the angular momentum of the bar with respect to this point O, from greatest to the least for the given situations. Okay, so this guy going straight means translate, and then rotate, translate. Rotate, you are rotating anti-clockwise, and this is your rotating clockwise. Translate, and this one is just a rotation going anti-clockwise for D. So now we're going to rank them and you're ranking the angular momentum of the bar with respect to the point O. And your point O, look at this, is even outside of that rod, okay, of that bar. And this bar is not attached to a pivot right here. So it's a very different system. Now we're going to rank it, so each one of them need to be written in its own equation. So the very first one, your point is here, your center of mass is right there at the center, and you do have your R, okay, and O separately times your MV. So when we calculate it by putting mass here, your length is going to be L because it's given to you, this length is going to be L. So we put that in there. And then your omega, which is your angular velocity, which is this guy right there. Yes. And then, of course, a constant K. So we ended up getting R is L, and we have another L from your velocity, this guy. We're just inputting that into this equation. Your mass is still there. And of course, this, your point O is outside of the rod, so therefore you do have some coefficient, which is just a number, to adjust that distance right here. And as for D, we're doing the same thing, starting out with the same. And here in this case, we do have a rotation, so we add the rotation part right there. Put it in, plug it in, and take K out of it, because it's still a distance away from the rod. Then you get that. And C, we do the same thing. You have a rotation, translation, so that's the translation part and rotation part. We do the same thing and calculate it, and we ended up getting that. And the last one, the same thing, you have just the rotation, so we start with the rotation formula, and then we're going to put your mass and then your L for the mass inertia, and divided by 3 because this is a rod with a pivot, so therefore the constant they change, and your omega, of course, is the 2 times of what we've been using here in this value. So this is what we get. So when you look at that 4 equations and consider, or what you consider, I'm going to go back and show you angular momentum. So I'm going to go back here, and you're actually calculating this, okay? So make sure we're not calculating momentum, but angular momentum. So therefore, again, you do the reverse thing again. So with the regular momentum, it is going to be going D, C, A, and B, because this is going to be the greatest momentum linear. Yes, so therefore, if you go separately, it's going to be the least, followed by the C, and then A, and then, of course, B. So when you flip it, you get B, A, and then C and D, because that one has the greatest, which is this guy, greatest angular momentum, because you have C. Both of them, we don't know what the K is, but we just take it the same, amount of the force that we're adjusting for that environment. And then, of course, A is going to be this guy coming second, and then C is going to be the next, and that's because of the direction changes. They're not the same because of this direction going in a different way. If you take this plus, then it's going to be negative. And then, of course, the least one is your D, because this is going to be pretty small, because its angular momentum is, because of this point O is not floating outside anymore, it is at this point, which is practically in parallel, in the same line as in G, like this. And if you want to go into the motion aspect, your rod is moving to the right, yes. If you look at the case B, moving to the right with velocity L, and your angular velocity. So this is linear equal to L times angular velocity, so that's how it's been moving, yes. and rotating at the same time, like that is going, anti-clockwise. So your speed is this guy, rotational speed. We call it angular velocity. So the full expression, if you solve all of this, you're gonna get like ml square, ml square, and then omega. So that's all what we're doing. So it's gonna combine both significant translational and then also rotational components. So the maximum total angular momentum along the case is going to be that. A is second, and that's because you don't have rotation here, yeah? So it's similar to B, but then the rotation, okay, is because of the point is about the same. I'm just, you can take it, that way, and then you have also translation here, yeah, but doesn't have a rotation about that point. So it is going to contribute less than the B, yeah, because rotation about the G point is not there, which is, see, less than that. So if you can't see this, you can just like I would say compare this to, yeah, you have extra IG here and this one doesn't. So we're just dealing with the translation here. And we have 2 points, so therefore you still need to consider that little bit of tilting kind of rotation is there, small rotation is there. And then of course it's less than B, but it's definitely more than C and D because it still includes both components, yeah? But the translation term is definitely less than C. And then of course your C, your rod is rotating, okay? And you also have a translation, but the rotation is in a different way. And that just, so angular momentum comes from your rotation, okay? And because of the directional change, you have a smaller angular velocity than your A and B. Of course, here you can see the direction, but again, don't forget your angular momentum is okay. Your angular velocity, okay, is very much vector. And then of course your D is spinning, like that at a pivot point O, and there's no translation, just a rotation. But then your point O is now on the same line as in G. So you have the angular speed is 2 times omega, and the moment of inertia is about O here, which is smaller, yeah? So if you think like that, so you have large translation with rotation, then you have a moderate translation but with rotation, okay? Or you have just a translation and not zero rotation, and you have rotation and translation, but it's a different direction rotation, and then you have a faster rotation without translation, okay? Lower inertia because of the point change is different, and no translation, yeah? So it goes B, A, C, and D. This is a little bit difficult for you to be able to understand unless you actually go into how the mass, all right, inertia changes according to the 2 reference points, yeah? It might need a little bit of time for you to be able to get this. Then we will go into angular impulse. So your angular impulse is the cumulative effect of a moment, and over time we're looking at it. So that's your impulse, and we have already talked about it. Because of angular, we use R times your force, and then we're looking at the time interval. Of course, we do our calculus operation integration, yeah? And of course, here is your interval, and this is your moment. You can also calculate in this way to get your angular impulse. So with rigid bodies, each individual force can act at a different location because your rigid bodies have sides, unlike particle sizeless. Angular impulse momentum principle, and the very first thing is this example. So here, you have to think about what happens when you take your finger and then spin a fan blade, okay, like that. And you're gonna go around with this angular velocity with that force you put it in to spin this fan inside. So when you do that, the impulse of that resultant moment acting on that body fan is going to equal to the change in that body's angular momentum. Okay, so we will put that into this equation. So that's your impulse and that's your change in momentum, because impulse is the change in angular momentum. We're dealing with the angular situation right now, and here is your moment. We're looking at that time interval. We're going to expand it to final situation and the initial, before putting the force to it, and after putting the force, and it goes around that fan with this angular velocity. So this is how you can be able to use the angular impulse momentum principle to be able to calculate, the factors that you want to calculate. Okay, so angular impulse momentum principle. In this principle, we will take a closer look at this pure translation with respect to a fixed point O. We can be able to write our moments at that interval, and we expand it, your final and your initial situation. And if you minus it, you're going to get a change. And that's what we're doing by using integration. That's just a mathematical operation describing that change. So your pure rotation about the fixed axis through point O, okay, and we can write it the same way, like that. It just we're abbreviating this whole thing into by using this mass inertia, and the angular velocity. This one is. All right, so general planar motion with respect to the body center of mass. You're going to get this. So you have your moment looking at that time interval, and then your mass inertia with your angular velocity final, and then of course initial, and you can get the difference, so you'll get the change of it. So that just dealing with a general planar motion, translation, or rotation, and with respect to the center of mass G, okay, which is indicated by this letter. And then of course you can also find it by using a different reference point, which is with respect to the fixed point O. So all you do is change the point, reference point here, and then we will use it the same way. Okay. Here just showing you general planar has a translation part, rotation, translation part, and then rotation. So this regular equation got expanded because we're putting translation aspect into it. All right, so the next example is, where should a force be applied on an object in order to cause the greatest impact on the object's angular momentum? So you want to apply the force to an object, and you want to cause the greatest impact on it, and because of that impact, you will have the object's angular momentum get affected. So if you want to hit the angular momentum, which is this guy, of course, you've got to think about these situations. So let's take a look at one by one why. So the very first thing we got to think about when we deal with the angular momentum is your where the reference is. So here at the geometry center of the object, so your R is going to be 0, or it will be very, very small, because your center is at 0. Because R, usually give you the torque because of that distance away from that reference point. Your minimum impact on the angular momentum, okay? So this won't give you the maximum impact. It will give you the smallest impact because your r is 0 because your reference point is at the geometry center of that object. And the second one is going to be at the object center of mass. This is not the same. This is geometrically, practically at the center. This one is the mass center. Yeah, the mass center is not the geometric center. Yeah, this is just a shape of that object. This is the mass of the object, and we're trying to find where the center of that mass is. So here, you're gonna have if you try to think like, will you be able to get the greatest impact on the object's momentum? No, you cannot, because your angular momentum change about that center of masses is 0. Yeah, meaning like you apply the force at the center of mass, it's going to cause a translation, not the rotation. Yes. The next one, at the edge of the object. Yeah, that is correct, because if you apply at the edge of the object, it would definitely create translation and the rotation. So therefore, you would definitely get the maximum torque, and also you're going to get the maximum change in your angular momentum. Yeah, so that's correct. And the last one is the placement makes this placement of the force makes no difference. That's not true, because the way that you place the force on that system, rigid body system, is very important, because they will create either translation or the rotation, translation and rotation. Okay, so the placement of the force depends a great deal to determine is that the pure translation, pure rotation, or the general planar motion. Okay, now we will get into systems or rigid bodies. So here you have your total angular momentum, and we always write it in this way, and that's your sum of the momenta of your individual bodies, and we describe with this little I, showing how many bodies are in there that you're dealing with. And of course we do the same thing, we expand the equation and we indicate we're dealing with the systems of rigid bodies by adding the I to it. So you're just basically getting the sum of it. Then we get into conservation of angular momentum. So here we need to understand that the applied moments is 0. So therefore, your angular momentum is conserved. Yeah. Now we're gonna write it, since the applied moments are the sum of the applied moments is 0. You can be able to write it this way. Since we write it this way, we can be able to expand it in that way. Yeah, it is the same thing. This is just using translation, rotation, before and after the same. Yeah, this is showing with the mass moment here. Yeah, your mass moment of inertia and then your angular velocity. Then we get into the next example with the Olympic platform diver. The person is initially rotating in a tucked position. They have like a different position before they dive. So doing a dive before unfolding himself prior to the entering the water. So he's gonna do this thing and dive it down like that. So if we neglect, this is water of course, so if we neglect air resistance, no air resistance, so the diver extend his body, his angular velocity, so it's going to go down with some sort of angular velocity. So we have to differentiate if that's going to increase, decrease, remain the same, or not enough information. So in order for us to do this, we have to come up with the conservation of energy. Conservation of angular momentum, and then we're going to write it this way with the mass moment of inertia and then angular velocity like this. And we will take a look at the angular velocity, which is this guy after the dive. So we will go over each one of them. Of course your textbook is going to give you the answer, but they won't give you why, so I will have to explain that to you. So the very first one is increase. So that's because the opposite of what happens when your angular I would say, let's just start with this mass moment of inertia. So when this mass moment of inertia increases, it's going to violate the conservation of angular momentum. So therefore angular velocity is not going to increase. in this case where the diver is from the tuck position and dive into the water. And thus, because we're studying the conservation of momentum, which is this guy, and every time you have your eye, okay, mass moment of inertia increases, you are not going to get this balance, in between before and after dive. So therefore, this is wrong. Angular velocity increases is definitely not correct. It will violate the conservation of angular momentum. B is decreases. Your angular velocity is going to decrease because it must decrease. It is because as moment of inertia increases, because that's the only way to keep this conservation of angular momentum to be intact. So if this angular velocity is decreased, then your mass moment of inertia is going to increase. And your mass moment of inertia, this resistance, is going to increase because he changes the position from tuck position to extend his body. So tough position is like that, extending his body become like that. So in that case, your mass resistance, mass inertia is going to increase. So when mass inertia increase, in order for us to preserve this conservation of angular, angular, I would say, like the whole thing, okay, the whole conservation principle to be intact. If you increase this, you have to reduce this. So therefore, angular velocity definitely decreases. They cannot be the same because your mass moment of inertia increases, and the angular velocity cannot increase with it. Also they cannot be the same, because that would definitely violate the conservation of angular, impulse angular momentum principle right here. Not enough information is provided. That's not true, because you do have enough information. It said it so your mass inertia is going to increase by changing the position from tuck position compact into extended position. So therefore the mass is going to increase with it. So to preserve this conservation principle, you have to decrease the angular velocity, because your angular velocity will automatically decrease as soon as this mass moment of inertia increases, in order for us to hold this conservation principle to be intact, to hold that principle. Alright, so for the previous situation, what happens to the diver's kinetic energy? If you think about in terms of kinetic energy, since the diver is diving into the water, you can't say like it stayed the same as he releases from the tuck. That's not true, because your kinetic energy cannot stay the same because he dives into the water. There's a big change in motion, because from the tuck position into the dive into the water, you do have a velocity. So therefore Ke is going to be different than it was before. It becomes larger when he releases from the tuck. So if we think about the linear kinetic energy with the linear velocity, you would choose B, but now you're dealing with rotation, because it changes from the tuck position to extended position. So you're dealing with a different movement than the linear. So there's a rotation involved. So that's the reason why C, it becomes smaller when he releases from the tuck position, is because your diver's rotational kinetic energy is going to decrease. Because this tuck position is better in rotational kinetic energy than the extended body position. okay? So this is correct and that's not correct because of the rotation position, which is your torque position. So A is wrong. It's because it doesn't stay the same, yeah, and because you do have the angular momentum is conserved, but not the kinetic energy. B is wrong because it said it becomes larger because the momentum of inertia increases because of the extended position of its body. Yeah, moment of inertia increases, but your angular velocity is going to decrease in order to reduce the kinetic energy. Yes. And don't confuse with the linear velocity. Okay, linear velocity is different from angular velocity, and when it comes to angular velocity you have to look for what position is going to increase it, which is the torque position, because that's the rotation. Extended body doesn't support the angular velocity. Yeah. And the last one is correct, yeah, because we get rid of A and B. Alright, then we will get into the eccentric impact. Your eccentric impact is just we're dealing with, a line of impact. We have already studied where the impact is here at the point of impact, line of impact, and then your plane of contact, for the collision. So the impact collision is, well, you're practically offset from one or both of that colliding body mass center, so like that, because of the shape of these colliding, okay, rigid bodies. So eccentric impact happens when the line of impact of that collision is kind of offset from one or both of that colliding body's mass center. So when you look at the mass center, is the here and here, it isn't on the line of impact. Yeah, it's definitely offset. Offset means it's shifted, away from that line of impact. At that time, you're going to get the eccentric impact. So if there are no external forces or moments applied to the bodies during the impact, or if they are small compared to the impact forces and moments, then we can assume that linear momentum and your angular momentum, all right, they are conserved. So we're going to bring our linear and the angular into it. This is after the impact. Before the impact is indicated by this little prime over your velocity. That's your linear and that's your angular. That's after the impact and that's before the impact. So you are going to get this way, yes. And of course, you have a conservation is going on before and after the impact. And of course, we are going to give our reference point, which is your this, okay, G offset point in this collision, making the eccentric impact. They're all the same. It's just your reference point is different, and if you measure from the line of impact, you're going to have that amount of difference in there. Okay, then linear momentum is conserved for each body along the plane of contact. Now when we study the plane of contact, we come to the linear momentum. So when you think about the linear momentum, that is your V, right? The reference point is at G, and you have your body A and body B. So that's what we're writing here. So that's before impact and that's after the impact. And you definitely have conservation, okay, of your linear momentum along that plane of contact. Then we will get into linear momentum. It's also conserved for the system along that line of impact. So here is your line of impact, and when you look at it, we can be able to see your linear, okay, which is your MVG is of A and B. They are definitely conserved. So that's after the impact, and this is before the impact. Now we're dealing with the two bodies, so A and B, and we're going to throw in our linear, okay, momentum at the point G. And the last one is the coefficient of restitution, as we always calculate by using, okay, the linear velocity. So we can be able to calculate this way. This is just a change in linear velocity after the impact divided by the change in linear velocity before the impact along that line of impact. And you can be able to calculate the coefficient of restitution. Alright, that's it for chapter 10, and chapter 10 is our final chapter. I give you 7, 8, 9, and 10 at the same time is because they tie to each other. Yeah.